Okay, I just want to illustrate what I've been talking in terms of compaction theory, how to make an engineered fill. So we look at various aspects of theory of compaction, properties of compacted fine-grained soils, what kind of field compaction and what kind of field compaction control we have. In the good old days, the people were using, they didn't have all this machinery, so all our kings, etc., when they had to build something, they were using a heavy animal like an elephant, and it used to be a good way of doing it. What does compaction do? It decreases future settlements, increases the shear strength, and of course also reduces permeability. This is because if you want to store water in a dam, a lot of embankments were built using soil, and you can make it into a dense material, and once you make it dense, the particles are so close, the void spaces are small, and you will have very small permeability. And this is the reason why we go for compaction. Just to give you compaction, if you have a coarse-grained soil, you can use only vibrations. As I told you at home, if you want to see how you can pack sugar or salt into a container, you pour it, then you shake it. The same thing is holds good for coarse-grained soil. For fine-grained or fine-grained soils, we can use falling weight and hammers, or you can even press it, but this is a very slow process, so we use this in terms of falling weight. A similar thing is used in the field. You have these vibrating plates, vibratory rollers to densify sands and gravel, whereas you have the shear foot roller, rubber tide roller, etc. in the field in order to get high density. So laboratory compaction purpose is to prepare the proper amount of water, mix it so that the resultant soil has a high denseness, and you would like to get the maximum dry density, and that is through impact compaction. Impact means I take a hammer, I drop it, or I throw it down, and that is what you call as an impact hammer. So these are the two principles. You would like to add the right amount of water, you get the maximum density, and you are using impact as an energy transfer. There are different types, but the standard is the standard one is this one, ASTM. You have the drop height is 305 millimeters, number of layers is 3, and number of blows is 25. Then modified one, which is again what we have changed is from 2.5 to 4.5 kg is the rammer weight. The mold is again 4 inch in diameter, which gives me, as I said, 1/30th of a cubic foot. And the drop height is increased to 450, and the number of blows is 25. So this is modified Proctor. Here you can see standard and the modified one. If you are doing on a larger cylinder to do the CBR test at a later stage, we use a 6-inch cylinder, and then we need to increase the number of blows from 25 to 56, and they get the CBR mold compacted. This is how a standard Proctor mold looks like. As I said, it's 4 inches in diameter, and the height is also approximately 4 inches, and this volume is 1/30th of a cubic foot. This is a collar. We add it so that when I compact it, the soil should fill not only the cylinder but come slightly into the collar, so that I remove the collar and cut it here, and then I'll have the whole Proctor mold compacted with the soil that we are interested in. So, and then this is the rammer, which is the actual rammer is inside, and this is the sleeve. You lift it with this handle so that when you lift from the bottom to the top, the height is exactly equal to 12 inches, that is 305 millimeters. So the weight of the rammer is 5.5 pounds. This is again an American measure. If you convert, it becomes 2.5 kg, almost the same. So what we do is we lift it and drop it inside the cylinder. We fill it first 1/3, second 1/3, and third. When I fill the 3 layers, it should come inside the collar. After compaction, The third layer will be about 1 to 1.5 centimeters inside the collar. I remove the collar and then scrape it. I get the top of the sample exactly equal to the top of the cylinder. This is how the compaction process takes place. Here is the cylinder, here is the collar. You tie them by means of a bolt so that they don't move, and here is the rammer, and he has just lifted, is about to drop. So just again specifications, the volume is equal to, where is the 1/30th, that's exactly what we said, and then the soil passing through this sieve number 4, and sometimes we go even finer fraction, 25 blows, 3 layers, 12 inches, that's how we do that. In case of modified, we go for 5.5 kg. Same thing again, standard Proctor test, 5.5 pound, 25, this is 2.5 kg, 25 blows, 3 layers, mold size is 1/30th of a cubic feet. If you want to calculate, the energy is equal to 12,375 foot-pounds per foot cube. In the modified one, you are increasing the height to 18 inches and the weight of the rammer is 10 pounds, which is about 4.5 kg, and then you also go for 5 layers. If you do that, the energy here is 56,250, which is more than 4 times whatever you are giving for standard Proctor. Of course, this is the energy how you calculate. The process of compaction would be you keep rotating the rammer all around. So in each layer you have to make sure you are covering the whole plan area uniformly. The first floor blows are given here, then after that you continuously do that. Okay, then you have to find out the water content and the dry density. And if I plot now, you can see here as the water content is increased from 10 to about 22, you can see that the dry density is increasing and it reaches a maximum value somewhere here. We may not always find out the exact. So when you draw this line or this curve, you have to fit in such a way that you get the maximum value properly. You can use one of the standard fitting curves or use your eye judgment, you get it. This is the standard Proctor dry density versus water content plot, and if I do the modified one, I get a higher dry density and a lower moisture content. As you can see here, the moisture content here is less than the moisture content with standard one. In the same plot, if I for example calculate for a given water content and different degrees of saturation, I can find out the density. And if I do that, if the soil is fully saturated 100%, which means there is no air, this is called the zero air voids line. What it tells you is that by compaction alone, you cannot remove all the air, but you will get somewhere around 90 to 95%, more than, at least here you can see 80 to 90% degree of saturation. You will never be able to remove all the air. So this is the point I would like to mention, and with increasing compaction energy, the line, blue line, keeps going up, which means you will have more maximum dry unit weight, which is attained at a smaller water content. Here the moisture content is around 17.5-18%, whereas in the other case it became, for a higher energy, it became 12. So if you want to do a air-filled pavement, you should add only 12% by weight of dry soil and apply higher energy. You get dry density of the order of 1.75, 1.9 grams per cc. And if you do ordinary one, you may get only 1.72. For different type of soils, if I see that, you can find out one is the well-graded loamy sand. That's a mixture of all sand, silt and clay, which is the best one. You can get as high as 2.1 grams per cc or million grams or kg per meter cube. So you got very high density and very low moisture content. As the clay content and fines content increase, moisture content increases and the dry density decreases. Please remember that heavy clay, if I look at it, 7, it has very low. So clay soils are very difficult to compact. So we don't normally prefer, we would like to combine, particularly like a well-graded sand with some fines, I'll get very high compaction characteristics. And the other one is, if the sand is poorly graded, it doesn't matter. Whatever water you add, the density will not be high. A poorly graded sand should not be used if you can avoid it. Then we also try to find out how the same from the lab can I do it in the field. So when I plot the same, you can see that in the lab I may get a higher value. In the field, I had to adjust the number of passes, the amount of energy, so that I can get this closer to the lab value. Once you define that, we have to do that. What you find is the soil here, when you have low water content, the particles are all separate. They are not close enough. Once you reach the optimum moisture content, the particles are much closer. And if you add water now, the water displaces the particles and they are far apart. So you will not get very good density. So in terms of structure, there is an optimum amount of water that you should use that will help in getting the best result. As I mentioned, the strength is maximum near the optimum moisture content, whereas permeability is very high when the soil is loose on the dry side of optimum, but once you reach the optimum, it more or less remains constant. So if you want a low permeability, better to go beyond optimum. If I want high strength, I should go for slightly less than optimum water content. Compressibility. Swelling also is a very tricky business. Yeah. The kind of equipment that we use in the lab, in the field, this is called a smooth wheeled roller, like the ordinary road roller you see, which is good for compacting the bituminous layers and the water, wet mix macadam, etc., but not for soils. But people try to use this, which is not a good thing. This is a pneumatic one. You see the tires are made of rubber with the treads, and this is better. This is for highway fills, dam construction. We are using this one for most of the soils. Then we have what is called as the sheep's foot roller. This is very good for compacting clay soils. It's like kind of a kneading, so that the soil particles are sheared and pushed in. So each foot attached to the drum pushes the soil inside. So that's why it's called the sheep's foot roller. This is another tamping foot roller, which is slightly different variation. This is a mat or a grid, a chain kind of a thing is attached or welded to the drum, and it also does something similar to sheep's foot roller. This is a vibrating drum, which means when he's doing that, the drum keeps vibrating, and we use this for sandy, coarse-grained material. So it gives vibrations and the soil becomes very, very dense. And then how do I control the compaction in the field? I need to find out both the dry density and the water content. To do that, we would like to know whether the soil is at the optimum moisture content, is it on the wet side, on the dry side. We have 3 methods: core cutter, sand replacement, and of course this is a nuclear method which we don't normally use it. In the core cutter, a cylinder with a collar is pushed into the ground. The soil fills up the cylinder, and again, like Proctor test, I trim it, take the weight of the soil, and determining moisture content is very easy. I can get the dry density very easily. This is how the core cutter, the collar, and the rammer through which I push the cylinder into the ground. This is the standard size, 100 millimeters by 130. Collar is 25 mm. It's called the dolly. In the sand pouring method, we make a hole. I like to measure the volume of the sand, the volume of the hole. So to do that, we have a cylinder in which I pour the sand. I know the density, so I know if I know the weight of the sand that goes inside, I can calculate the density. So what is done is I first remove the soil here, find out the weight. So I know the weight of the soil I removed. I need to know the volume of the soil. So what I do is I put a sand cylinder, allow it to go in here, find out the volume of the sand, filling it from the density. That is how we do that. Sometimes now we are also using, instead of sand, I put a plastic sheet and then add water, which is easy because the sheet, again, this excavation we do may not be exactly geometric, so a sheet will fit in and the fluid will go. I know the amount of volume of the fluid that fills up, and that's how we find it too. These are the indirect methods wherein I can now use the nuclear methods too. So using all these techniques, we try to control what is happening in the field.